Hello everyone, today we'll talk about the problem number of atoms. As you can see, the code barely fits the screen, so you know we're in for a fun time. This is quite a natural problem. We're given a chemical formula, which just follows the natural rules for chemical formulas. So it has names, which consist of uppercase and maybe some lowercase letters. It may have a number after a name of an atom. And it can also put those things together, so take a formula, which may be a concatenation of multiple atoms or atoms coupled with the count, put parentheses around it and put a count after it, or maybe don't put a count after it, that's also a valid formula. And what we want to do is we want to transform that formula to a simpler form, which is just the total form, where we have sorted by name all the atoms, and after them we have their cumulative counts, assuming of course that those counts are greater than 1. So H2O is just H2O, because H is before O in the alphabet, and that's it. But for more complicated formulas, especially with nesting, we have to do some multiplication, because for instance in this case have H2, O2, and also this whole thing is taken 3 times, so we have 3 times 2 H's, so 6 H's and 6 O's. So in essence, the difficulty and the annoying part of the problem is that we have to parse this first representation and evaluate the expression that it represents and return the result, which the result is of course those total counts. And when you're parsing something, it's typically useful to arrive at the grammar yourself, so define the grammar based on the requirements in the problem, and then use a parser generator, use some library that can do the rest for you, that can, for instance, generate a parse tree, and then you walk through the parse tree. That's still a lot of code, but you don't have to at least do the parsing yourself. But in this problem, we should do the parsing ourselves, unfortunately. However, what you can notice about this grammar is that it's very simple to parse. While it has some nested sub-expressions, so that's something that we should keep in mind. At any point, we know exactly what we're looking at, and we don't have to care about backtracking, changing our previous decisions, and so on. So for instance, if you look from the left, then you know that you can either expect the start of a name, for instance an H, or you can also expect an opening parenthesis, and that's it, nothing else. Again, after a name, what can you have? You can of course have a closing parenthesis if there was an opening parenthesis later, but if you see a digit, then you know that the name has ended, and now a count is starting. Perhaps that digit is the only digit, perhaps there are more digits that are number larger than 9, but still, you can look at the type of the character and you know exactly what you should parse at this point. So the last part that we also have to decide on to make things a bit simpler is that we might go from left to right and maintain both the total count, the global count, and also the count of the current expression. And then if we have a closing parenthesis and a count, then we take all our counts, multiply them by the count that's after the sub-expression. But that means that, for instance, if we have very deeply nested values, then for all of them, so if we have n over 2 depth of nesting and n over 2 different atoms within it, then for all of those atoms and for all the levels of nesting, we would have to have a quadratic number of operations of multiplying them together to get the final count of every atom separately. That's not the problem in this problem, but still, it's pretty much better form to do something about it. And it's very easy to do something about it because since the counts follow the thing that they're giving a count of, then we can, instead of going from left to right, we can go from right to left. We still can easily parse everything, but now we'll know the count before we know what the count is for. And that means that we can keep those counts as a stack and know at every level what the final count is. So whenever we encounter an atom, we know exactly how deep it is nested and what the final count of it will be to add to the global counter. Otherwise, the situation is very standard. So if you want to pause to make sure that you understand everything and to think about how you would implement this parser before we jump into the code, now is your chance. Because the rest is just implementation. So we have here our code. We will be maintaining the count of every atom so that at the end we can return the result. The final representation will be the name of the atom and the count, assuming that the count is greater than 1. We just get the final representation of all the atoms that we've counted, and of course we have to sort them by their name. So that's easy. Now we'll also use two helper functions for all the portions that consist of the same type of character. So for the counts, which are all digits, and names, which are all letters, we can just use a helper function. So to parse the digits, parse the count, we will take a list of digits, take the digits of the end of our formula, append them to our list, then reverse that list, convert it to a string, and then convert it to an int. To parse a name, it's almost the same thing. However, we first of all have to make sure that the formula has not ended, but that doesn't really matter actually in this point, because we know that we'll be taking lowercase letters for as long as they are available. At the end we also take another letter, which is the one uppercase letter in the name, and again we join the reverse of those letters. So those are the helper functions that will make parsing a little bit briefer. Now we have a little bit of evaluation logic. We have this current multiplier, which is the multiplier that will be applied to the next thing that we see, and also the nested multipliers for multipliers in conjunction with parentheses. This is a list because we'll be keeping a stack. So for instance, if we're nested 3 deep, then we have 3 different values for those nested multipliers, and whenever we exit a pair of parentheses, we get rid of the multiplier corresponding to the insides of that pair of parentheses. And now we parse the formula. For as long as there is anything to do, we look at the end, and this is where the simplicity of the grammar comes in, because we can just look if it's a digit, if it's alphanumeric, or if it's 1 or another parenthesis. And we know exactly what to do in all of those cases. So, if it's a digit, we know that this is a multiplier. We don't know what to do with it yet, but we know that it is a multiplier. There are two options. If what then comes before it is a name, that multiplier applies only to that name. Otherwise, it will be a parenthesis, and the multiplier will apply to everything within this parenthesis. Then, if it's a letter, we parse the name. We take the current multiplier, which is by default 1, multiply it by the multiplier for the nesting depth that we're in. By default it's 1 if we're not nested anywhere. So that's this multiplication, and we forget the multiplier that applies exactly to this single name. Otherwise we have parentheses, and the situation is very simple. We take the parentheses, and if it's an opening parenthesis for us, so a closing parenthesis means the start because we're going from the end, and an opening parenthesis is an end of the group. So when the group starts from our perspective, we append the current multiplier. Again, it's 1 by default, but maybe we've seen a multiplier just before. So in this case, here we have a 3 before a parenthesis. So when we encounter this closing parenthesis, we'll have current mul equal to 3. So we append the previous nested multiplier multiplied by this multiplier that we've seen, and of course now we've used up this 3, so we forget that it's there. And of course when the group ends, we get rid of the last multiplier, which applied only within that group. So this whole parsing loop is now very simple. Those two are very easy auxiliary operations that express something very simple, that a number consists of digits, that a name consists of an uppercase letter and maybe some lowercase letters after it. And of course the transformation is simple, and we talked about it before. So the problem is not that difficult, at least to come up with. There are no tricky edge cases, I think, but still implementing it is pretty much a slog. But yeah, so if you didn't implement it, at least it goes pretty smoothly, so give it a shot if you want.